Hello, my name's Thanom and I'm from UNSW. Today I'm going to work through some of the Math 1011 calculus problems from the section on integration. So question 1b is asking us to find the indefinite integral of 4x plus 2 to the power of 16. So an antiderivative. We're looking for an antiderivative of this power function. It's a power of 16. So if we look at our standard integrals, some of which I've written over here, then I know that to find an antiderivative or an indefinite integral of a power, I want to add 1 to the power and divide by that power. So perhaps, since this is a power of 16 here, so perhaps the answer is going to be 4x plus 2 to the 17 multiplied by 1/17. Okay, after all, this is a power function here. However, if we wanted to check that, we would differentiate it. So we suspect this might be the antiderivative. So let's differentiate it to see what we get. So this differentiates to, well, if I was going to differentiate, I'd bring down the power. That would multiply by that 1/17 to give 1. I would reduce the power by 1. And the chain rule would say that in addition to all of that, I would need to multiply by the 4 here. Okay, so this isn't quite our answer because this differentiates to 4 times as much. 4x plus 2 to the 16 times 4. So if I want to anti-differentiate this, if I want to reverse that chain rule, I really need 4 of these for my answer to be 1/17, 4x plus 2 to the 17. I can't change the question though, so what I'm going to do is multiply by 4 and multiply by 1/4, so I haven't changed the question that I've been given. And now this 1/4 is just a constant, I can keep that there, and this, an antiderivative of 4x plus 2 to the 16 is just 1/17, 4x plus 2 to the power of 17 plus a c. The idea being that the inside of this function, the derivative of the inside of that function is 4, and that 4 is sitting outside there. So I can reverse this chain rule at this stage and get this as my answer here. Question 1d is asking us to find the indefinite integral of 2 over 40 plus 5 here. The first thing I'm going to do is actually just write that 2 out the front. The antiderivative of 2 over 40 plus 5 is just the same as 2 lots of the antiderivative or indefinite integral of 1 over 40 plus 5. And I can just see my functions a little bit more clearly. I have 1 over this function 40 plus 5 here. I know 1 over integrates or anti-differentiates to a logarithm, natural logarithm of the absolute value of that denominator. So I suspect, right, perhaps the answer is ln of 40 plus 5 here. So if that was the answer, then this should differentiate to this expression here. However, when we differentiate this, we do have to apply a chain rule. So this actually differentiates to 1 over 40 plus 5, 40 plus 5, but the chain rule says that in addition we would need to multiply that by 4. So in fact this can't anti-differentiate to this because 4 lots of that has to anti-differentiate or integrate to ln of 40 plus 5 here. So if I want to be able to find this integral, I actually need 4 times as much here. So I actually need 4 times as much to anti-differentiate it. I can't just change the question, so if I multiply by 4, I'd better divide by 4 so I don't change anything. And now, since the derivative is sitting there, just like this, I know that anti-differentiates to this logarithm. So I know this now anti-differentiates to ln of the absolute value of 4t plus 5, and 2 over 4, that's just a half plus c. So we can see it's 1 over a function, and I know 1 over a function anti-differentiates to a logarithm, but we just have to be careful reversing the chain rule, because the logarithm actually differentiates to 4 times as much, so we need to make sure there's 4 times as much there so we can anti-differentiate it to ln of 4t plus 5. Question 1f is asking us to find an indefinite integral for e to the 4x plus sine x here. So the first thing I'm going to do is rewrite this as 2 separate integrals. This is just like finding the integral of e to the 4x and adding the integral of sine x dx. Now, first of all, let's integrate this e to the 4x. Well, e to the power of x integrates to e to the power of x. So we might suspect that e to the 4x would integrate to e to the 4x. So perhaps e to the 4x is going to be the answer for that first one. But remember, this differentiates to 4 times as much. This actually differentiates to e to the 4x times 4 because of the chain rule. So this can't quite be our answer because 4 lots of e to the 4x anti-differentiates to e to the 4x here. So if I want to be able to find an antiderivative there, I really need 4 e to the 4x to be able to reverse the chain rule, but I can't change the question, so I will put a quarter out the front. The key is that the derivative of this 4x is sitting here to reverse the chain rule. I'll just rewrite this one. We can do that one easily last. Okay, so we have a quarter, and I know that 4 e to the 4x anti-differentiates to e to the 4x there. So this anti-differentiates to e to the 4x, and sine anti-differentiates to minus cos. So this is minus cos of x, and then we'll just plus 1c on the end. So this is a reverse chain rule here. Now you'll see that if you look at your standard integrals, the standard integrals, some of them have some constant a hanging around. So it actually tells you that e to the ax anti-differentiates to 1 on a e to the ax. So it's a very specific case of reversing the chain rule here. So you could have applied that directly and said e to the 4x anti-differentiates to 1 on 4 e to the 4x just by using this. So that's perfectly fine, but what we're really doing is reversing this chain rule, which requires us to have that derivative sitting there to be able to anti-differentiate them. In question 1i, we're asked to find the indefinite integral of sec squared of x on 4. So sec squared we know anti-differentiates to tan. Tan differentiates to sec squared, so sec squared anti-differentiates to tan. So perhaps our answer is tan of x on 4. Right? But this differentiates to, if that was the answer, we would want it to differentiate to the question. But when we differentiate tan of x on 4, we have to remember the chain rule, because tan differentiates to sec squared, but in addition, we'd need to multiply by the derivative of x on 4, which is a quarter. So in fact, a quarter sec squared of x on 4 anti-differentiates to tan of x on 4. So to find this indefinite integral here, I would need really a quarter of sec squared of x on 4. But I can't change the question, so if I multiply by a quarter, I have to multiply by 4 there. So the 4 is going to stay around at the front here, and I know a quarter sec squared of x on 4 anti-differentiates to tan of x on 4 there, plus a c. The key being that the derivative of this inside function here is sitting here so that I can reverse that chain rule. Question 1k is asking us to find the indefinite integral of 1 over 16 plus 9x squared. I can see that in this form here, that's going to be an inverse tan. So I know that 1 on a squared plus x squared anti-differentiates or integrates to 1 on a inverse tan of x on a. Here, I don't quite have x though, I have 9x squared. So there's a couple of ways to deal with this integral. One method would be to actually take a factor of 9 out of this denominator. So if we take out a factor of 9, I might put that outside the integral there, then on the denominator I'll be left with a 16 on 9 plus a single x squared, or in other words a 1/9 dx over, this is 4 on 3 squared here, plus an x squared. So if I rewrite it in this form, then it exactly looks like an a squared plus x squared on the denominator, where the a is 4/3 and the single x is the single x. So I can use this standard integral, the form of that standard integral there. So the 1/9 is out the front, and I know according to my standard integral page, the antiderivative or the integral of this is 1 on a, so 1 on 4/3 inverse tan of x on 4/3 there, plus a c. I can neaten that up because that's just a 1/12 out the front, and this is inverse tan of 3x over 4 here, plus a c. So that's one way to deal with the fact that that was a 9x squared on the bottom. Alternatively, we could deal with that 9x squared a completely different way. Right? We might think about this integral as dx over 4 squared plus a 3x all squared. And we're after finding an antiderivative of this. This is almost in this form, it's just we've got a 3x instead of an x there. So perhaps the answer is 1 on a inverse tan of this 3x over a. So perhaps this is our antiderivative here. If we wanted to check that, we would differentiate it. If I wanted to differentiate it, I have to do a little bit of work. This a quarter is going to stay here. Inverse tan of something differentiates to 1 on 1 plus that squared. Right, so 3x on 4 all squared. In addition, the chain rule says I would need to multiply by the derivative of the inside function, so I'd need to multiply by a quarter. This 4 by 4 is 16, so this simplifies to 1 on 16 plus 9x squared times by a 3. Right? You can see there's an extra 3 here. That didn't have the 3. So if I wanted to anti-differentiate this in a different way, I could have multiplied by 3. How do I want to write this? I might write it as 1 on 4 squared plus 3x all squared. I could multiply it by a 3 and multiply it by a third, so I don't change the question. But essentially I would need this derivative here sitting there to be able to reverse this chain rule. Okay, so I know 3 times 1 on 16 plus 9 squared anti-differentiates to this function here. So the 1/3 is here, and I know that this anti-differentiates to a quarter inverse tan of 3x on 4 here, plus a c, which we can see is exactly the same as this 1/12 inverse tan of 3x on 4 plus a c. So that's just 2 different ways of dealing with this 16 plus 9x squared on the denominator of that integral.